We're doing the Ultimate Go tour here, and it's been a long day. It's been a hard day. Some days are harder than others, but I'm gonna sit down and I've got it's, what time is it? It is 9:22 p.m., so I got like 30 minutes. So I wanna share with you about constants. That's what we're gonna do in this video. And you could get to, it's the next step in the Go Tour, the Ultimate Go Tour. You could get to the Ultimate Go Tour by going to tour.ardenlabs.com/tour/list. And there's a whole series of videos here and a repo with code and great README files, which feel like a book. There's so much information in them. So the link for all of the videos in the playlist is down below in the description, as well as the link to the repo. And the repo is at goes to11 GitHub. My username is goes to11 on GitHub, my user account. And then go to Learn to Code Go version 3, and then go into the BR000 BRBK Go Tour folder. And then here you'll have an index to like all the different steps we've taken with links to the videos and links to READMEs for each of them. Plus there's coupons for the courses and code review checks, which are really important things to know, gleaned out of each of these things. So I'm just going to record this straight through, and learning about constants in Go is one of those things where it's really easy just to blow right past it, and it's easy to say, oh yeah, okay, those are the mechanics. That's how you declare a constant, right? Like, here's how you declare a constant. Here are the mechanics. Totally easy. Constant, my true equals true, or constant 0 is equal to 0, or positive int is equal to 42, or negative int is 42. It's easy to blow past that, and also you could come in here and you could specify the type. I'm just looking to see where's one where I specified the type. So here I specified, the type. So you could specify a constant with a type like that, which, starts to kind of raise some curiosity if you're paying attention, right? Like constant pi float 64 and constant pi, right? Like, okay, why is it that you can specify type and here there's not a type? Starts to raise some questions. But a lot of people will stop right here at the mechanics. They'll be like, all right, I know how to do a constant in Go. But there's actually a lot to really know about constants. And in this video, in I don't know however much time it takes, you're gonna learn kind of like why constants are so cool and unique to the Go programming language. And you're going to learn about how they relate to numeric literals, because numeric literals are also untyped constants. So we could have typed and untyped constants. So we're going to learn all about that in this video. And the takeaways are right here. So we're going to learn about that stuff. And then the table of contents with like additional information is great. There's some great additional information there. So you could pause the video and you could take a look at that information there, because that's what we're going to cover. And then also there are these great quotes right up top. Something I just want to point out about the Ultimate Go Tour is I just learned this. You could go into dark mode here. So there's dark mode. That's kind of fun. Like I came and it was night and it was like, wow, we're in dark mode. I'm going to leave it, actually, I don't know. Yeah, I'm going to leave it in day mode. And then I'm going to scroll down here and we're going to go into the constants, because that's the one we're working on. And then there's going to be a description here that Bill put together, and then my videos and my descriptions and my READMEs enhance this material. And so it's my take and perspective and teachings on what Bill's put together here. But you have some examples over here. Notice that there's multiple tabs. And if you click run on one of these examples and nothing happens, the server's asleep. So just after you've hit run, hit refresh, and then come back over here and hit run again. I'm just going to go back to day mode, and it'll give you what you need. It'll run it for you and show it to you. All right. So the first thing I want to start with is right here in the takeaways, and that's that constants can be typed and untyped. And so to see that, we'll just come over to VS Code, and I'm in the BRBK Go Tour folder in 06 constants and 00 live main.go. And so constants can be typed and untyped. So I could do a constant, and I could say that this is going to be A, and it's going to be equal to 42. And I could also do a constant, and I could say that this is going to be B, and it's going to be an int, and it's going to be equal to 43. And so this first one here is an untyped constant. And this is also known as, AKA, also known as an untyped constant. It's also known as a constant of a kind, because there's this idea of things being of the same kind, right? Like it's a numeric. And so you can look to see, like, is this constant? if it's untyped, what kind of a kind does it belong to? Does it belong to the string kind? Does it belong to the numeric kind? And if it's the numeric kind, is it like the int or the float kind, right? So what kind of a kind does it belong to? So when I was, learning about constants and going deeper with constants, one of the things that kind of threw me is I'd hear people talking about the language, and I'd hear, like people who really knew what's going on, I'd hear them saying, it's a constant of a kind, it's a constant of a type, that's kind promotion. I was like, what are you talking about, right? And so an untyped constant is also a constant of a kind. And if you go in and you look at well, here I have this code here, but if you look at the reflect package, and so down here I have some code with reflect, I just need to find it. And it's right here. So we reflect value of, and you could run this kind, like what kind is it? But that will give you output just like type does. But it's kind of interesting just to see that. So that's a little bit maybe of the source where this word kind came from. And then this is a typed constant here, right? So we're specifying the type. And so when we print both of these, and I'm just going to print them out so my linter stops complaining. And I'm going to copy that and bring that down. And when I print out A and then print out B, and then here I'm going to do like F, and I will do in these here, I want to see, and I'll get rid of that one actually, and I want to see the type. So %T, tab, %V, and then a new line, and I want to see the type of A and the value. And then also we'll do that with B. And so now I'm going to run that. Did I get my extra B in there? I did not. There we go. And when I run this, so make sure I'm in the right directory and then clear this out and go run main.go. When I run this, I get 42 and 43 and that they're both ints. And so here during compile time, the compiler will implicitly convert whatever this is, whatever value that is, into what it thinks it should be. And so when you have an untyped constant, which is also known as a constant of a kind, when you have an untyped constant at compile time, the compiler will do implicit conversion. It's implicit conversion. We're not being explicit about it. We're not saying take this value and now convert it to this type. Right? Take this value of one type and convert it to another type. We're not being explicit about it. It's implicit conversion. And so that occurs at compile time. And so, right, it did that at compile time, and it implicitly converted 42 to an int. Well, this is what's interesting about it. So if I come down here and I make a function, I'm going to call this function float me. And in float me is going to take a float 64 and float 64. And it's going to return a float 64. And then when I do this, I'm also going to use the short declaration operator. So we'll do C, and we'll do colon equal, and we'll do 30. And so then I'll come back down here, and I'm going to bring this down. And since we're doing with constants, I'm going to do var C is equal, constant C is equal to 30. And so when I look at this, right, when I look at C, I'm going to see exactly what I saw before. And that's going to be, it's going to give me the value and then also the type. And now I need the return in here. It's missing a return. So I'm going to return F, and I'm going to multiply that by 2.5. And now I'm going to run this. And it's an int and it's 30, right? So 30 is an int. So if I come down here now and I'm going to, receive the variable that's returned, the value that's returned, and store it in that variable, float me, and I'm going to pass in 30 here. And we've seen that 30 here is an int, right? So the compiler implicitly converts that to an int. And now when I do this and I run this and I bring this down, and now I'm going to change all this right here to be f me. That's kind of funny. And so there we go, right? That's kind of funny actually for this situation. And so I'm going to run this now. And when I run this, I'm going to get, that's a float 64. And so here the compiler said, all right, this untyped constant, I'm going to implicitly convert it to an int. And that makes sense, right? 30 looks like an int. That would be the conversion I'd make just looking at it. But then here when I pass it in, a 30 again, which is another numeric literal. And so we're talking about numeric literals here, and this is what's really interesting. And so just like take 30 for an example, and 30 is a numeric literal, and that's also, numeric literal is also known as, a numeric literal is also an untyped constant. Numeric literal is also an untyped constant. And so these numeric literals, and this is like one of the really important takeaways of constants right here, right? We're able to use numeric literals throughout our program, right? Just put a number in, and these are untyped constants. And then at compile time, the compiler is going to look at what is the numeric literal here, this untyped constant, and what type should it be? What makes sense for this situation? And so in this situation, what made sense for this, unique numeric literal right here, what made sense was that's going to be an int. And what made sense for this unique numeric literal right there is that it's going to be a float 64, right? It's going to be a float 64. And so that gives us a lot of ease of programming, and that's one of the goals of the Go programming language, is to have ease of programming. And that's why there's this quote right here: implicit conversion is one of the features that make Go both strongly typed and convenient to use, right? And then this quote down here is also great. This is from the Go language specification. An untyped constant has a default type, which is the type to which the constant is implicitly converted in contexts where typed value is required. For instance, in a short variable declaration, such as I is equal to short declaration equal to 0, where there is no explicit type. The default type of an untyped constant is bool, rune, int, float, 64, complex 128, or string respectively, depending on whether it's a bool, rune, integer, float, complex, or string. But you could even take something that's looks like its default type should be an int, and it'll be a float 64 if that makes sense for the situation. So the takeaways, the first takeaway here: constants can be typed and untyped. And untyped constants are also called constants of a kind. And untyped constants can be implicitly converted at compile time, right? And numeric literals are untyped constants, right? Numeric literals are untyped constants. And so let's further explore this. There's some code. And if we come over here to 00BRBK Go Tour, this code will shed more light on it for us, right? So coming into 06 constants, there's another main Go. We were just at the main Go in 00 live. Now we're going to look at the main Go that's in 06 constants. That's right in that folder. And so I put all this code together here just to kind of show you some stuff about constants. And so these are all untyped. We're not specifying the type. And these top two, right, I'm just showing how there could be an int or a string or a rune. Here's another rune. Here's a bool. Here's some bit shifting, right? Here's a float. Here's another float. And I also want to show this constant declaration block right there with the parentheses. And then I print all that down through H. And here I'm printing out and showing the bit shifting, so you can look at that and inspect that. Hey, we're in live. No, we want to come up out of live. You could inspect that, on your own time. See how that works. I'm going to go run main.go this and scroll on up. And so the output for that, right, is right here. There's the binary output right there, and then G and H. And then also here, seeing the type of H. And so right here, mathpi times mathpi. One of the cool things, mathpi is like a really big number. And here we just multiplied mathpi by mathpi. What are you talking about, right? And so one of the cool things about, about constants is that they have 256 bits of precision. That's a lot of precision. And so if you come in and look at the language specification and you look at constants right here, so right here I'm at the top of the language specification, and I go down to constants right here, integer constants with 256 bits, right? Floating point constants, 256 bits, right? Wow, that's huge. Because if we look at the numeric types, so come over here and look at the numeric types. The numeric types aren't that big. So I'm going to look in numeric types right there. And the numeric types aren't that big. And so one of the things which is really cool about constants is you could do really high precision, big number calculations during compile time, right? During compile time, you could do those calculations. So here, during compile time, when it's not a runtime cost of efficiency, you could do a really massive calculation and it'll get that answer for you during compile time and it'll store it. And then here, right, I'm printing it out. and printing out that answer, and I'm seeing the type here. And so that type, right, the math pi times math pi is right there, and then printing out the type, and then printing out the type with more precision. And so this is from the FUMPT package. You can see how to print with precision, but here I'm saying 50 decimal places or 100 decimal places, right, for that float. And so there it's printing out all of that, and there's math pi to, it goes out to, I guess, like what, 48, 49, 48 decimal places, and then it just gives you a bunch of zeros. And so that's just more of kind of seeing, you know, constants at work. And so here we have some more stuff, which is interesting. We'll just kind of continue just to kind of explore this code. But here we have an implicit conversion, right, or kind to integer. And the kind of this, right, the type of this here is going to be float. Those are just the defaults. And then down here, we're specifying the type here, specifying the type. And then down here, when you have numeric literals, which are untyped constants, numeric literals, which are untyped constants, you're going to get kind promotion. So here, if we have a float, and this one would be normally an int, they're both going to be float. So you're doing math with the same type and maintaining that integrity. And here, this is going to become a float since this is a float. And here, since this one's an int, that one's an int. And so sometimes what you'll see is like, you know, if you need to look at the decimal place, and so I'm just taking a look at this right here and wondering why it's not giving me a lint error, because 1 divided by 3 is going to give me, 1 is going to give me 0.333, but that will print out as 0. And so just to see that that prints out as 0, I'm going to bring this up here, make a copy of it, and bring that up. And I'm going to make this we are here 1. And the next one will be we are here, just we are here. And so when I run this, we are here gave me 0, right? So I guess it's all right with that. But if I make this, turn this into a float, I thought that would, oh, so there, wait, it gave me my compile error there for a second. Okay, there's my linter, right? It's not a compile error, it's a linter error. It's like, where's my linting error? And so it just tells me the result 0. The result 0, because it's an int, there's no float 0.3, right? And this is an int, that's an int, so you're just going to get 0 here. Is that what you wanted? That's what the linter is telling me. But if I make that a 3.0, that becomes a float, and then this becomes a float. It's just like this one right above, and then it will give me the decimal place, which is this one right there, right? And so if I run this again, we'll see that. It's going to be exactly the same as the one right above. And we are here, there we are here, right? It gave me that one here. But if I take that out, they're both going back. They're both going back to being ints, and that's just going to give me a 0 because ints don't have float decimal places, right? And so here is a constant that's of a type, and the type there is int8. And so when I come down here and I do y times 2, right? Well, this is an untyped constant, it's a numeric literal. And so the compiler is going to look at this and say, well, this is int8. I'm going to make this one int8. And then the answer is going to be int8 right there. So that's kind of cool. And if we look at that one, we could see the answer is int8. And then we have constant AAA and constant BBB. And just doing that reflect value of, and then the type. And then here we have that float me example again, right? Where I'm passing in 30 as a float 64 into that and getting back, you know, float 64. And then we have max int here. And so max int is just showing you the max of an int. And what this is, if you look into the types here, the max int is that number there, 922.337, 922.337. Like that's the max int for an int 64, right? And that's for signed int 64. So it's going both sides of 0. And for unsigned, it has the U in front of it, just in case you've never come into what the difference between an int and a uint is. One is unsigned and one is signed. So the unsigned is just positive, but the signed has the negative sign. It goes from negative to positive. And then all 256 characters, 0 to 255 is 256 numeric characters. And the reason it's 256 is it's 2 to the power of 8. 2, 4, 8, 16, 32, 64, 128, 256, 8, right? 2 to the power of 8. And it's a uint 8, right? Uint 8. And so it's got, 8 bits that it can use to store numbers. And so it's going up to 200, and from 0 to 255 are 256 numbers. But the reason we came here is because to see this large number, that's the largest number of a signed int 64. And we could just see here that constants can deal with much bigger numbers. And so if I have this constant here and then I try to print it without like reducing it, I reduce it to 1/10 its size, it'll throw an error because that constant can't be printed here, right? Cannot use bigger untyped int constant as int value and argument to print line because it overflows. So when you see that overflows, it means you got a number bigger than what could be stored there. So if I just put in that, multiply it by 1/10, then it shows it. The next thing which is interesting to know about constants is this concept of iota. And so iota will increment things. And so here we have A, B, and C. And if we come down and look at what A, B, and C print, we come down here and look at iota. Here's where iota is printing out. And so there's A, B, and C, right? 0, 1, 2. And so when you establish iota, it just increments up. It goes 0, 1, 2. And you can also do it like this, where you just have iota, and then the rest will just understand that they're going to be ioted also. They're going to receive iota also. And so DEF also, once again, gives us 1, 0, 2. So I'm just showing it both ways because this is the way you normally see it. And what's going on, is that, right? You could do it either way, but this is the way most people do it. And it's just understood that you want iota on those two. And iota as a constant can be useful for doing things like bit shifting. And so here I have a little explanation of bit shifting. And if you look at this here, what that is doing, and we come down and we look for that bit shifting, we have that right here, right? And so if I change this from 10 to like 2, and then we look at the output, we could see that the bit shift went over 1, 2, right? And it went from the 1's place to the 2's place to the 4's place. And so that's what this bit shift did right there. And if we change that to decimal, right? So we could also add in the decimal here, do this, do a tab, and then do a percent D. My eyes can't see the keyboard like they used to. And I'm going to Control C, Command C, Command V. I'm a recovering Windows user. And finally gotten back to the Mac. If I run this once more, I have 0, 2's, and 4's place. So the decimal of that is 4's. And if I make this 3, it's going to shift that bit over one more time, right? And so I'm going to shift that bit over one more time. And I'm shifting the bit twice there, once for the binary, once for the decimal printout. And so now it's there and it's 8. And so that's bit shifting. So you could use bit shifting down here, and you could bit shift over 10 times, whatever the iota is. And so iota here is going to be 0. This will be 1, and then it'll be 2, and then it'll be 3, and then it'll be 4. And so when it does that, it'll go 10, 20, 30, 40, and it's going to shift the bit over that many places. And then that can give us kilobytes, megabytes, gigabytes, and terabytes. Because if you think about the difference between these, it's 1024. And so if we have 2 to the power of 10, that's going to be 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, right? And so that's like moving that bit over 10 places. 2 to the power of 10, right, will give us kilobytes to megabytes to gigabytes to terabytes. And so that's printing out all those bits right there, and then also the decimal equivalent right there. All right. Next thing to know, and I'm going to stop my camera and then restart because it only records so long. I'll be right back. The next thing to know is about the Math Big package. And so the Math Big package allows you to do really precise calculations, but they can be, at the expense of efficiency, and they can be processing intensive as you start to get into big calculations. But if you need really high precision, there's a package Math Big. So you could just Google Golang package Math Big, and it'll come up. And so here's a little example of using the Math Big package and saying from the big, I want a new int, and that new int's going to be 0. And then I print that out, and I get right here, right? It's put out BI right there to help us find the place. I got 0, and then I'm going to set the bit and shift this over 255 times. And so when I do that, I get this massive number right here. And so that's printing out that number right here. And then I create a little function here, add commas. So we could add commas every 3 times. You can see how big that number is. That's big. So if you need to do really high precision calculations, I don't know what that'd be for, you got the Math Big package, and that's good to know about. All right, so now that we've seen some code and gained a little bit of understanding into how constants work, coming back here and just looking again at these takeaways. I've already been through these, so just pause and put the video and read through that again. But then also this one here, typed constants limit precision. And so we saw that as we went from an untyped constant, we were able to have a really big number. But then as we put a type on something, we overflowed. And then so as you type something, you're limiting precision to this as you give something a type. But when it's untyped, you could do much higher precision. And so when you have a typed constant, it limits precision. And then we'll also look at scientific notation, mantissa, and E down here. So I just want to scroll through here. These are the mechanics. You could come through and look through them. We've already gone through all the mechanics, but it just shows you how the different types can be put together. And then understanding constants talks about typed and untyped constants, and you could see, typed and untyped right there, and also shows you how you could do it with this, in a single declaration right there. And then we learned about enumeration constants, Iota, so we saw that. And a little bit more there about constants and making code more readable, and then understanding this idea of kind. So we've talked about that, where that comes from, and we learned that numeric literals are untyped constants, but here's a nice little description of that if you want to read through that, and it gives some really good information about it. And then constants have high precision, right? So that gives a little more information about the high precision of constants, and they provide type safety and inference, and allow you to do advanced calculations. And then constants also provide some portability to different architectures, which is cool. And typed constants limit precision, right? So when you give a type to a constant, this kind of illustrates that. So you could hear untyped and then typed, and precision being limited. And then scientific notation, mantissa, and E. And so I found that not everybody knows this, and so I didn't know it at one point. And so you'll sometimes see notation like this with an E, or you'll see notation like this. So 3.45 times 10 to the power of 2 would just be like 100 multiplied by that. So that would be 1, 2, or 345. And 3.45 e to the 2 is exactly the same as that, right? So that's what the scientific notation is, and that's what the E notation is. And then when you see mantissa, that's referring to that number at the front, right? That's the mantissa. And it gets into mathematics and formulas beyond that, but sometimes you'll see that phrase mantissa. And then you could go big with math big. And so there's some more information about math big and a couple of examples. And then that is, and then rational numbers. It talks about rational numbers. And so rational numbers is just another phrase for fractions. And then we have width and precision. And so we already saw this where we could set, how precise do we want our decimals to be with the F formatting verb. And then the math big package has arbitrary precision, which sounds like that's not so great. But the term arbitrary precision refers to the capability of handling numbers with an arbitrary number of digits, right? Limited only by the available system memory. So it means that you could have really high precision. Depending upon the machine, it'll be arbitrary how high that precision is, but you could have really high precision. The very essence of success is practice. And so that's Jan, I don't know how you say his last name, but there's a nice quote, and there's coupons here, I'll come back and tell you about it in a second, but there's a nice quote from him for the beginning. He was a pianist and a politician, and he signed the Treaty of Versailles, which ended World War I. And so I love this quote by him, though, here. If I miss one day of practice, I notice it. He's talking about being a pianist. If I miss 2 days, the critics notice it. If I miss 3 days, the audience notices it. I think that's a great quote. And there's a beautiful picture of him, which I'll get here into the README so you can check that out. All right, if you want to learn more about the Go programming language, you can check out Bill's courses right here. You can check out my courses right here. Bill's like intermediate to advanced. I'm like beginner to intermediate with some advanced stuff. And this right here, use this link for me, because that link is a special link which will give you better pricing. And then this link right here for Bill, if you follow it, and I'm just going to do an incognito window here, it'll take you into his classes, and you can enter discount code and put in my name, Todd McLeod, And I don't get any kickback for that other than, you know, friendship and doing a friend a favor. And Bill's been super great to me as a mentor and a teacher, and he's helped a lot of other people. And so you'll get a special discount. It'll be a surprise. So go there and put it in, see what kind of discount you get. And if you still can't afford that course, his courses after the discount, here at the Ultimate Go Tour, when you're in any of these areas, like we were just in Constance, you could click on scholarship form, and then you could fill this out, and you could just tell Bill a little bit about your situation. And he's a super giving guy. And if you're in some part of the world where, you know, all you can afford is $5, let him know. And chances are he'll give it to you for free. All right, so that's a little bit about Constance. It's good stuff to know about, particularly that thing about constants being typed and untyped, and how the compiler will do implicit conversion during compile time, and how numeric literals are also untyped constants, right? Those are like the really important things. Numeric literals are untyped constants, and that gives us a lot of ability as programmers to, you know, write code in a really easy way, so it's convenient to use, ease of programming, but it still keeps things strongly typed. And so that's pretty cool. All right, that's a bit about Constance. Hope you're having a great day. See you next time.